Morning, everyone. So yesterday we introduced starting to draw Lewis structures. Basically, Lewis was a nice shortcut to the Bohr model. We know for reactions to occur, atoms have to collide, and during collisions, it's always going to be the outer shells that actually collide. So it really is only the valence electrons that actually do the bonding. We did start off a little bit here with Lewis structures on ionic compounds here. Again, you can still, even though it's not part of the real definition, you can still use that nice memory aid here. Typically, metals tend to have very large radii, whereas your non-metals, which I'm going to say X, typically have very small radii. You should be able to explain that based on your chapter 3 stuff there. And based on that here, if you look at the trend here on electron activity, this would relatively have a low electron activity, not very good at tug-of-warring, whereas the other one here would be a much higher electron activity. I mentioned here, these guys here, they end up colliding, and as they collide, they potentially could have shared an electron. It's unpaired electrons that potentially do the bonding here. Everything wants to pair up. Everything wants to pair until they have a noble gas stability, a full shell sort of stability. But it turns out because the tug of war here is against a lightweight and a heavyweight, the non-metal pulls so hard that it completely snatches the electron to itself. In that case there, because the electron has completely been lost, the metal has been oxidized, the metal now reverts down a shell. It's now lost the outer shell. I don't draw that shell anymore. But because it is charged, just a recap from there, metal with the positive charge, and the non-metal, which is now stolen the electron, might go on to steal even more electrons than that here. One thing here is I can't actually recognize which electron actually currently belong to the metal, but I know that the X now has one extra electron, and we end up with the Lewis structure here, positive, negative. We know for your ionic compounds, they end up forming an ionic lattice. So not too much in terms of drawing Lewis structures for ionic compounds. They end up forming lattices anyways, and they end up packing either directly one on top of the other, or more so like a tetrahedral. They call it closed cubic packing if you want to look into it more detail. Specifically, most of the chapter is dealing with covalent compounds. So if you notice that your compounds are nonmetals and nonmetals, you don't necessarily need to check electron activity. You would just go with it. It's probably going to be covalent, so probably just our old single bonds, double bonds. One reminder is you want to make sure you include all the dots, and you're going to find that the more practice you get with Lewis structures, the faster you'll be. You'll probably even recognize some structures, so you don't need to necessarily always follow the rules from scratch every time. But definitely a good place to start off, because a lot of our theory that comes, it's very theory heavy in this chapter. It's going to be based off of Lewis. So we're going to see in the next lesson, starting off from Lewis, we're going to do VSEPR, which starts predicting the geometries. We're going to do hybridization and polarity. All of them start off from the grounding of Lewis, so all of them assume that you can do Lewis structures very well. In fact, a lot of people find this chapter challenging because, let's say on a paper 1 multiple choice question, they might just ask you, okay, arrange these guys in terms of bond angle, or arrange these guys in terms of bond length. Before you can answer any of those style questions like polarity, things like that, you have to have the Lewis. So if I can emphasize it for you, practice your Lewis structures so that you're really, really fast at it, and then you're going to see a lot of familiarities as we go through the chapter. So on that note here, I will practice some with you here. I asked you to draw the carbon monoxide molecule from yesterday. Hopefully you were able to do that. Today, let's try drawing CO2, and let's try drawing SCI4. So again, do a mental check for yourself here. These ones here all happen to be non-metals, so I'm expecting them to be covalent. Pretty much the compounds I'm going to give you will be covalent anyways, so you don't need to worry about them necessarily having charges or electrons transferring. We're more so worried about is it single bonds, double bonds, and the geometry. So starting off here, remember we could brute force it. These are still fairly simple molecules. I'll show you one more that's brute force. So what I mean by brute force is go to your periodic table. Carbon is on column number 14, so that means 4 valence electrons. Oxygen is column number 16, so 6 valence electrons times 2. That gives you a total of 16 valence electrons. Carbon is supposed to come in with 1, 2, 3, 4. Oxygen should be somewhere around it. Single, 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 single. I'm going to pair 2 of them. And likewise here, single, 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 and pair 2 of them. So this is what I'm referred to as a brute force. I have not taken the valence electrons, collected them all up, and then followed the arbitrary rules. This one, it's carbon, you have 4. Oxygen, you have 6. How can you guys bond so that you guys end up satisfying the octet rule, having a full shell? So satisfy the octet. In this case here, again, it's a relatively simple molecule. You didn't have this problem with the carbon monoxide from yesterday, but we can do the unpaired electrons, those bond, oh, double bond on the left. or those bond, double bonds on the right. Because these electrons, don't get transferred, we can double count them. The oxygen on the left side thinks it has 2, 4, 6, 8. The carbon thinks it has 2, 4, 6, 8. The oxygen here thinks it has 2, 4, 6, 8. And everyone is happy. So basically it's double-double. We started seeing in yesterday's lesson here, sometimes brute forcing it doesn't work. The nice advantage of doing a brute force is you can identify whether there's actually any coordinate bonds. Let's compare this to trying to do the same molecule but doing it with the rules. The rules started off the same here. You would actually collect up the same 16 electrons. No doubt the final picture should only have 16 dots on there. We're going to plop down them. Usually your molecules will only have one center, and usually the least electronegative one you only have one of, and this is one going to be in the middle. So I have C. Our rules say connect the oxygens with at least a single bond. No, I don't care geometry in this lesson. We'll worry about that in the next lesson. Starting off with a single bond, every single bond is 2 electrons. Out of the 16 that I have, I've used up 4. Now I'm down to 12, so keep a running tally here. Then you start making your guys outside to inside, happy with a full octet. I'm going to add 6 on the outside here, and 6 on the outside here. If you're keeping a count here, I've just run out of electrons. At this point here, the oxygens on these far sides here are perfectly happy, but the carbon, this one here, is not happy yet. Carbon, even if it does double count the single bonds sharing these electrons, carbon currently only has 4. It doesn't have that full shell stability. So what ends up happening here is we saw that with our rules, if you run out, and that's the only time you do this, if you run out, that's when we start making multiple bonds. That's when we start considering doing double bonds and triple bonds. If I have extra, there's no reason to do this. So in this case here, what we're going to do is we're going to take the 2 electrons on the oxygen. This is currently a lone pair. I'm going to squeeze it in. In chemistry, we like things that are symmetrical. Technically, it could have even been another lone pair squeezed in, a triple single. But let's squeeze in a lone pair on both sides, and let's make it that double-double. In that case there, with our diagram, C double-double like this. It's not a correct diagram until you have all the lone pairs, all those extra dots there. Maybe I'll draw the ones for you so you can see it better here. That is now a correct Lewis diagram. Our rules also got us to the correct final picture. The carbon is in the middle. It's double bonded on both sides, and it has a satisfied octet in that fashion. Even though your rules always make it look like this one here, oh, I'm taking 2 electrons, both electrons are coming from one neighbor, it looks coordinate. When you do it the brute force way, you see that no, when these ones here actually bonded, none of them actually was a coordinate bond here. You can only tell coordinate bond here from brute force. So make a note to yourself here, we had no coordinate bonds, even though that's what sort of looks like when we follow the rules. That's for the CO2 molecule. It's a double-double. On this side here, let's do SCI4. I would just go straight to the rules. Usually, if the molecule is not simple, your brute force method doesn't really work. And usually, they don't ask you, is there a coordinate bond in every question anyway? So let's just go straight to the rules. Selenium is in group 16, so it has 6 valence electrons. Iodine is halogen, so 7. I have 4 iodine, so times 4. 7 times 4 is 28, plus 6. I'm going to collect up 34 electrons, put them in a bag. So now selenium has no electrons, iodine has no valence electrons, nobody has their own electrons anymore. I'm going to plop down a central atom. Since I only have 1 selenium, and it is the least electronegative, let's plop down the selenium first, and let's surround the selenium, connect the eyes with at least a single bond. Again, I don't currently care the geometry, but we're going to see in the next lesson with geometry, usually the most symmetrical picture is correct. So we have this SEI4 here, selenium being surrounded by 4 iodines. So far, I've used 2 electrons for every single bond. Keep that running tally here. 34 minus 8 is now 26. Work your way outside to inside. So put down the dots. Everyone here would need 6 extra dots because in addition to the single bond, then it would have 8. I would have added 6 times 4, 24. And now, after subtracting 24, I still actually have extra. One easy way to count it is you can even count it. I have 8 this way, 8 this way, 8 this way, 8 this way. So 8 times 4 is 32. Well, I had 34 to go with it. In this case here, this is the opposite problem. I have not run out of electrons. So do not come along and start squeezing it in or whatnot. I have no desire to do that. In fact, what ends up happening is if I have extra, our rules from yesterday here said extra, put these extras, so put on the central atom. And we're going to see that as one of our exceptions today. Basically, what's happening here is we're actually expanding its octet. Selenium was actually already happy with the 2, 4, 6, 8. It's perfectly happy with the noble gas stability, but seeing as my diagram is supposed to have 2 extra electrons, I would just put those 2 electrons somewhere as a pair, and it doesn't matter which corner that I add it. Now selenium, it's correct, it actually has selenium with 10 electrons. It's beyond its 8 octet, it's actually now an expanded octet. So there we go. Just make sure you practice through those list of rules here, making sure you're getting more familiar and getting quicker and quicker with drawing these Lewis diagrams. Today I just want to flesh out a little bit from yesterday here. With any good rules, again, there was no chemistry in these rules here. There's always going to be chemicals that don't obey these rules here. So this is us basically going in real life, taking real measurements of bond lengths and bond angles and seeing times where our current Lewis model doesn't really fit. And what we're going to do is we're going to modify, oh, this molecule doesn't fit, and here's why it doesn't fit. Here's something you need to be aware of when you try to follow your rules with Lewis structures. So today we're going to do 3 styles of exceptions. So we'll just call these exceptions here. Again, the geometry is not going to matter in this lesson. We're going to do geometry as a whole separate lesson tomorrow. So for an exception here, we're going to start off on the small side. Let's deal with an incomplete octet. So octet was familiar to us. Octet is 8. Everyone wants a full shell. There are elements that are actually stable with an incomplete octet. They don't quite have 8, but they're happy. They don't want any more. So in this case here, we're going to make, I'm going to make a reminder here. These are typically going to be small atoms. So towards the top of the periodic table, I'll list out for you which ones they are. Small atoms that are stable with less than 8 electrons. 8 would make you that full shell, but there are some things that they're actually happy with 6 or 2 or 4 or whatever. They actually don't want 8, don't force them to have 8. We actually saw this a little bit on yesterday's lesson here. If you look at your periodic table here, just sketch these up for you here. If you look at hydrogen and helium, those two are already exceptions. These ones here are currently on n equals 1. The first shell can only max out at 2. So although yes, we do want this behavior of maxing out having 2 electrons, these ones here don't necessarily want 8. So far for hydrogen and helium, these ones here are perfectly happy with just 2 electrons. That actually makes sense that it makes the fact that H has to be what's referred to as terminal. H has to be on the side of the molecule. By the time H makes a single bond, that already is H's 2 electrons that it needs. If H were somehow in between the molecule, H already would have 4 and would not do this. So that makes H, it has to be hanging off the side of the molecule here, only with a single bond. That's the only time that bond shows up. Helium, we don't, unless I'm actually asking you to draw the Lewis picture for helium, we're not going to see that too much. Hopefully you're able to remember, well, this is a noble gas. This one here doesn't really bond anyways, and because it doesn't really bond, there's no sense in drawing compounds that have helium inside. But there you go, that's one exception here. Hydrogen, helium, these are incomplete octets because they aren't quite 8. Truly speaking, lithium here would actually be an incomplete octet as well, but lithium here is getting into that sort of, well, lithium is a metal, he's going to lose really badly. What turns out for lithium is lithium usually just transfers the electron. There isn't this variety. Lithium is going to revert down a shell, it's going to have 2 electrons like the hydrogen helium, but we're really not going to run into it too much. Lithium is just going to end up being positive, like I showed you earlier, and fluorine here is a regular octet, so that's 8. So don't really worry about lithium. It's going to be 2 electrons just like before. The 2 other small elements I'm looking for here are going to be, we have beryllium here and we have boron. And this is just experimentally found. Even though beryllium here is technically a metal, remember the stair-step line is over here, we're picking up a little bit closer to the covalent nature. So it turns out experimentally, not only memorize hydrogen and helium are 2 electrons, beryllium in most of its stable compounds, beryllium only wants 4 electrons, and boron right beside it, that's already crossing over, it's into the metalloid region, closer to the nonmetals. Boron actually only wants 6 electrons. Notice how I'm writing these ones here. Beryllium, most stable, will have 4 electrons. That could be beryllium with 2 single bonds, that's 4 electrons. Or beryllium here with a double bond, that's also 4 electrons. It's just experimentally we find, don't force beryllium to have 8, even though it technically is shell 2, and that's based on the fact that this is a fairly tiny atom. It can be stable with less than 8. Boron, similarly, it's stable with 6, so that could be boron with 3 single bonds. That could be boron with a double bond and a single bond like that. We will run into a compound where boron actually ends up having 8 electrons. That actually would be a less stable form of it. I'll show you how you can test why it's less stable later on, but the most stable is actually boron with 6. So this is experimentally, you're going to draw a compound. Let's actually do a compound here. Let's say BF3. As you follow your rules, you're going to say boron is 3 electrons, fluorine is 7 times 3. Boron trifluoride is supposed to have 24 electrons. Plop the boron down and the fluorine somewhere around it. Again, I don't really care geometry, but looking ahead, usually the most symmetrical picture is the correct one. I connected them with a single bond. 2 electrons make up a bond, 1 from each neighbor. I have 18 more electrons. Make sure you include all the dots. These are all lone pairs. They're not currently used to attach things, share things, but those are definitely needed. I've now seemingly run out of electrons. If this were any other element except for boron, I would say, well, the outer guys are happy, but the boron is not happy yet. Because boron, now I'm telling you, is an exception, boron currently does have 2, 4, and 6. Boron is actually happy. We have not run out of electrons. This is exactly the molecule I want you to draw. So experimentally, when they go take a picture of boron trifluoride, they end up measuring these actually to be the single bond lengths between a boron atom and a fluorine atom. Single bonds all range in different sizes depending on which elements are actually bonded together, and that shouldn't surprise you because every element has a different radius. So these are incomplete octets. These are exceptions that you have to follow. Don't force beryllium to have more than 4, boron to have more than 6. You could temporarily create molecules that might have 8, but super unstable. The other exception here, well, those ones there were less than 8. There are exceptions like the molecule we did in our warm-up question here. 2, these guys here are actually happy with more than 8. So an expanded octet. 8 would normally be stable. Small things we're happy with less than 8. We would generally say it has to be bigger things that actually are stable with more than 8. I want to emphasize here, expanded octets, it really only starts at sort of period 3 and lower. So period 2, period 1 cannot expand. Some of those even are incomplete octets. But what we're going to do here is period 3 and below. So period 4, period 5, different rows. The larger atoms, these ones here, period 3 and below elements, can, I want to emphasize that, it's optional, can hold more than 8 electrons. We're going to see in a later lesson is because it actually utilizes some of those d electrons to actually do some bonding. Up to this point, we've been saying d electrons are inner electrons. They're not valence. They're hold really closely to the core. But once I'm shell 3 and I start getting those d orbitals inside, I can somehow promote those d electrons and somehow utilize them to hold them more than the traditional 8 that the s and p electrons hold. That's another reason why it has to be period 3 and below. So roughly speaking here, based on our periodic table, so we have our hydrogen and helium. We're starting off just on row number 3. So this is n equals 3. These ones here would be 3s, and these ones here would be 3p. I'm mainly looking at covalent compounds, so I'm mainly only looking at nonmetals. That doesn't leave you with a lot. It only leaves you with these guys that might hold more than 8. There will be cases that these guys here only have 8, perfectly fine. The question here is, how would I know? Basically, you don't need to memorize this one. You just follow your rules here. If you found, earlier I didn't even give you this language of expanded octet, if you find that as you're following the rules, we still ended up with extra, I told you to put them on the middle, and now the interpretation is, oh, it's expanded. It actually now has more than 8. I didn't need to tell you that. In another compound, Se might have 8, perfectly happy. So while an incomplete octet you must follow, it's 2, it's 4, it's 6, those ones here are sort of guarantees, whereas an expanded octet here, starting on row number 3 here, they really like asking you like phosphorus. I'm going to emphasize for you, phosphorus can have 8. There's many times it's just a regular octet, totally happy. Don't force it to have 10. But in this case here, you will find some compounds where phosphorus, like the selenium for earlier, it actually is stable with 10. Sulfur, similarly, I want to emphasize, there will be many compounds sulfur is 8. How will I know for certain? I need to go experimentally and actually measure it, see if it's an exception or not. Based on our Lewis structure stuff, based on our rules, we basically, if I have extra electrons or if I need extra attachments, I would definitely need more than 8, and I would interpret it. Maybe it's utilize some of those inner orbitals, inner electrons to do the bonding. So let's start off with the compound here. I'm going to link a YouTube clip where Jamie from Mythbusters actually tests out this SF6 molecule. but for time being here, I'm just going to see if I can draw this SF6. Right away, alarm bell should be ringing in your head here. I have 1 sulfur, and supposedly we're attaching to 6 fluorines. Let's see how this works out in terms of the number of electrons here. Sulfur is group 16, so 6 valence electrons. Fluorine is 7 times 6. 7 times 4 plus 6 is 48 electrons. I generally, for molecules, will only have 1 central atom. The least electronegative would be sulfur. Fluorine is really high electronegativity. Imagine surrounding the sulfur from all sides. I've already expanded sulfur's capacity, because every bond is already 2 electrons, and that already means sulfur already has 12. So be it. If sulfur is supposed to hold 6 fluorines, it has to have an expanded octet here. If you drew that on a test here, you won't get marks for that. What's missing here is all the lone pairs. Even though they're non-bonding pairs, even though they're currently not used for bonding, you do need to make sure you dot up all of them there. At that point there, I've used up 48 electrons. I can do an easy count of that. I've used 8 this way, 8, 8, 8, 8, 8. I've used 8 in 6 different directions, and basically that's 48. So this one I didn't even have extra. I actually perfectly ran out 48, but you see that it's expanded because sulfur has to hold on to 6 attachments. Again, on the Mythbusters, you can see what happens to his voice when he breathes this in. No, we don't have this, but it makes for a good demo. Hypothetically, you might be asking to yourself, okay, especially with this one here, couldn't it have been, let's say, S, and let's say all the fluorines ended up as a row? Technically, there's nothing stopping you from drawing a Lewis picture. We were just following this list of arbitrary rules here where there should be just 1 center, but what if it was a long snake-like molecule? What if it's sulfur and I have a long chain of fluorines? What if they actually weren't all attached to sulfur, or some of them were attached to this side, some of them attached? I wouldn't actually know. This is something that Lewis doesn't really do a good job of it. Lewis just cares. You have a certain number of valence electrons. Make sure whatever drawing you have has everything having its full octet and has all the valence dots on side. It actually doesn't decide against why couldn't it have been this molecule. So with our third exception here, it's not really an exception, but what I want to introduce to you is another tool that we have at our disposal to try to help us pick out why isn't it this long chain, and why is it more likely going to be just having 1 center surrounded by everything. So again, not quite an exception here, but a nice tool that we use. I'm going to introduce to you something called a formal charge. Formal charge, we can use FC for it. Just give you some understanding of this one here. For a formal charge, this one here, they aren't real charges. So these are assign charges for bookkeeping. And basically what we're going to do is we're going to test the compound. I want to test whether it really is just 1 central atom or whether it's a long snake-like molecule. I usually do this formal charge only when I'm unsure. Could it be this one or could it be this one? Let's go back to that CO2 molecule just so that you can see how this works out here. When we were doing the CO2 molecule, as we were working through our rules, we had 16 electrons. We were at a point where we had this picture. I had run out of electrons. We know from our rules I'm supposed to drag the electrons in. So let's drag the electrons in on one side. That would give you, like this. The carbon in the middle would be slightly happier. And then what we said is, using a symmetry argument, because it was a double bond on the left side, let's put a double bond on the right side as well. Hypothetically, it could have been this electron pair here also dragged 1 electron in. Hypothetically, it could have actually been O like this, C, and O like this as well. If you ask Lewis, both this picture and what we would consider the correct picture, the symmetrical double-double kind of picture, both of them have everything having 16 electrons, so all the dots are accounted for, and both of them have a full octet. So according to Lewis, this is a correct picture and this is a correct picture. But we know experimentally they can't both be correct. It can't be, in this case, your triple bond with that high electron density, I'd expect it to be a lot shorter, whereas a single bond is a lot longer of an arm. A double-double is sort of more even on both sides. If I have to pick, when there is this ambiguity, I don't know which one is it more likely. You can do this formal charges. You can assign some fake charges just for bookkeeping, just to test out which compound it is. In your textbook, they give you a really complicated formula here. I'm going to simplify a little bit here. For the purpose of formal charge, when you're testing it, imagine these bonds here are separated exactly in two. Realistically, whenever I have a bond, let's have a bond between X and Y, I know there are two electrons, and I know based on electronegativity, let's say Y is more electronegative, I know the electrons are leaning towards the Y, maybe not enough to get transferred. I know it's not evenly shared. But since formal charge is just a tool that I arbitrarily assign anyways, I'm just going to pretend the bonds are exactly evenly split. This electron was yours, X, and this electron was yours. So when I have a triple bond, I'm going to imagine one of these electrons on the left side are oxygens, the other set of electrons are carbons, and I'm going to do it that fashion. So for formal charges, make the assumption bonds are split exactly in two. Then what we're going to do is we're going to test each element one by one, and my formula is going to be, for formal charges, for that element, take the number of valence electrons you usually have and minus off how many, because I'm testing my drawing, how many does your drawing have? Again, this is a slight simplification. In your textbook, you have a little bit longer formula. I find this one is good enough. So here's what I mean. I want you to go up to each element itself, and I want you to just go, okay, oxygen normally has a valence of 6. I know in the Lewis picture it actually has 8. That's not what I'm talking about here. But normally you have a valence of 6. And so far, since I've cut the bond, so far I've drawn this oxygen having its own 1, 2, 3, 4, 5. If I imagine the 6 minus 5, it's like oxygen has a fake +1 charge. It isn't really positive. But this is just a tool that I use to try to figure out, is it going to be the molecule on the left or the molecule on the right? So this one here is a +1. You do the same on the middle one here. Carbon is usually a valence of 4. I've drawn it having 1, 2, 3, 4. I don't care which side it's on. Great. The formal charge there is 0. It's like having no charge, which has no charge. The oxygen on the right side, which is single bonded. In this case here, again, we have, normally oxygen has a valence of 6. I've drawn it having 1, 2, 3, 4, 5, 6, 7. 6 minus 7 gives you a -1. It's like this one here has a formal charge of -1. Now, first thing I want to emphasize again is these are not real charges. We have not actually transferred electrons and actually formed an ionic bond. What this does give us, however, is a slight imbalance to this molecule. If I took what's called an electron density map of this picture, if this really were the picture, I would imagine one side would be seemingly more negative and the other side would be seemingly more positive, even though no electrons have been transferred. These are not real charges. Another observation you can make here is overall CO2 is a neutral molecule. If you add up all the formal charges, they should always be the same as the total charge. In this case here, 0, +1, 0, and -1 cancel out, so 0. So that matches up. Let's test the other picture while we're at it here. The carbon in the middle has 4 valence electrons. I've drawn it having 1, 2, 3, 4. I know it still has 8 in terms of the full Lewis picture, but this is just rules that I'm doing just for formal charges. This time when I test this picture on the right hand side here, oxygen has a valence of 6. My drawing has 1, 2, 3, 4. 1 of the double bond, 1 of the double bond, 6 minus 6, this is now 0. If you tested the other double bond, oxygen, also 0. So again, the total charge here adds up to the total charge. 0 plus 0 plus 0 is the total charge 0. All the electrons should have been accounted for, so that doesn't surprise me. But now in comparison these two pictures, whether it was ambiguous, should it be this picture or should it be this picture, if you had to guess, we know charges are unstable. And if you had to guess, one of them has formal charges, one of them has a 1 and a -1, while this one here has no formal charges as well, usually the picture with least formal charges is the correct one. So I've taught you how to assign formal charges, and we're now using the language of, because the charges are unstable, usually when we have formal charges, when I say smallest formal charges, I mean closest to 0. I don't care positive or negative. Formal charges closest to 0 indicate the preferred structure. So without actually going in real life and actually measuring it here, formal charge is just a tool I can use to decide, is it likely this one, is it likely this one? And lo and behold, if you actually go out in nature, even though Lewis predicts both of these to actually be correct, in this case here, it's actually going to be the length of a double bond. It's even on both sides. We're nonpolar. This is actually the preferred structure. So you don't need to check formal charges for everything. Usually when you follow the rules, say earlier I had gone to SF6, I had gone to BF3, usually by the time you follow the rules and you put down the central atom, usually this one here will have the least formal charges anyways. If you don't believe me, you can go through and actually assign formal charges. We really only do formal charges when we're sort of unsure. We're not sure, should it be this one or should it be this one here? I'm going to end off with one old paper 2 question here. This is actually a nice example. I want you to draw the Lewis structure for N2O. Now, they could just ask you simply like that. In this one here, because it was a paper 2 question, they gave you some ABCs. They gave you sort of what you're targeting. You can use that as a sort of map at what you're trying to calculate next. In this case here, what it says is when you draw this molecule here can have 2 different connectivities. So 2 different connectivities. 2 different ways this one here can be ordered. I can either have the connectivity of N, O, N, which I would expect based on the symmetry argument, or because I have 2 N's, I could also have N, N, and O. Again, based on the symmetry argument, I'd say, well, why would I even bother considering this one? That's not symmetrical. Why is N in the middle? Now, N is actually the least electronegative, so that sort of hints maybe it's this one here. But so far, let's just go with it here. There's 2 different possibilities. Because we're ambiguous here, we can check for more charges to figure out which one is it likely going to be. So let's go through here. N is group number 15, so 5 valence electrons times 2 plus the 6 here. This diagram should have 16 like carbon dioxide. So by the time I draw this picture, I run out of electrons. Again, just go with the symmetry picture. Let's drag the electron pair in. Let's drag the electron pair in. Lewis would say that's a correct picture. You have the 16 dots all accounted for. Everyone has an octet. Everyone's happy. Same thing happens on this side, a double-double. You can follow your rules there, exactly the same as carbon dioxide. Lewis would say this is a correct molecule as well. Again, we say, well, they can't both be correct. We know that when atoms are bonded differently, they're going to have totally different properties. Because they have different properties, I need to know which one is it more like. So here's another case of formal charges, maybe to the rescue, maybe to try to decide, is it going to be the left one, the right one? Sometimes, believe it or not, formal charges also gets it wrong, so it's not a super crazy tool that always works, but in most cases, it's another tool that we have at our disposal. So here's what we do here. We're going to assign formal charges. I'm going to test each atom one by one. So let's test this one here. Formal charges is the number of valence electrons you usually have. You minus off how many have I drawn. So that's the formula I'm going to use to test each of the elements one by one. I know that overall they have a full octet, but just for testing formal charges, I'm going to pretend to cut the bonds exactly in 2. Formal charge for N usually has a valence of 5. I've drawn it having 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1. It's like this side is negative 1. This side is symmetrical, so also negative 1. Oxygen has a really bad formal charge. Usually has a valence of 6. So if I've drawn 1, 2, 3, 4, 6 minus 4 is a plus 2 formal charge. Now, what's not bad is they do add up to the overall charge. The overall charge, this molecule also is neutral. 2 negative ones and a plus 2 is also going to be 0. But what's really bad here is because these were fake charges, I'm not really saying that these sides are negative and this is actually positive, electrons are transferred. This charge here is actually humongous. Happens to be positive here, but it's really big. Let's test the other molecule and let's see if it's any better. So here we have our double bonded nitrogen again. 5 minus 6. 5 for valence, minus off the 6 that I've drawn here. Again, I know that as 8 overall, but just for formal charges, I'm going to assign these ones here. That's a negative 1. This is 5 minus 1, 2, 3, 4. You don't need to show this math if you can just do that in your head here. In this case, you're not showing the math. I'm going to go 6 minus the 1, 2, 3, 4, 5, 6, and lo and behold, I have 0. Again, the formal charges, they add up to the overall charge. 0 plus 1 and negative 1, they add up to 0. That just means all the electrons are accounted for. Again, Lewis said both of them are correct because they all have a full valence shell. But when I look at this here and I use this sort of generalization, when I have smallest formal charges closest to 0, charges are unstable. If I have a picture that has least formal charges, I tend towards that direction. So when I look at these ones here, this one has negative 1, and a plus 2. This one here is negative 1, plus 1, and a 0. Because this one here actually doesn't have any 2s, I actually, for this molecule and this molecule only, I actually would prefer the actual asymmetrical molecule. And again, lo and behold, when you actually go look at it in nature, it actually is the asymmetrical one. Sometimes symmetry actually gets it wrong. Now, one last thing that's a kicker here. Because we're dealing with asymmetry here, there were actually 2 other possibilities. When we actually, so we're sort of deciding against that one, probably not the O in the middle, probably the least electronegative. Usually when you have the least electronegative in the middle, your formal charges are better. By the time we were drawing our Lewis picture, remember we had this when we ran out of electrons. Just like with carbon dioxide, it could have been one side actually triple bonds. I could drag these 2 electrons. I could have this. That would be a correct Lewis diagram with the N and O conductivity, or it could be N. I can have N, single bond N, triple bond on this side. If you check the number of valence electrons, Lewis would say all three of these are correct because they all have 16 electrons and everyone has a full octet. So again, 4 more charges to the rescue. We already said, strangely enough, it's the asymmetrical picture that actually takes it this time, but seeing as it's asymmetrical, well, this is also asymmetrical, this one's also asymmetrical. Test out the 4 more charges and see which one do you believe it's going to be. So let's just have a look here. This one would be 5 minus 5. So this one here has 4 more charges of 0. 5 minus 4 is a plus 1. 6 minus 7, right, it's going to be a negative 1. So that one looks good. This one here, 5 minus 7 would be a negative 2. 5 minus 4 is a plus 1. 6 minus 5 is also a plus 1 here. That's why it's super important to have all the dots so that you can count which electrons belong for the 4 more charges. In a similar vein here, I would ignore this last one here. Probably not a single bond of nitrogen because, again, I have a big 4 more charge. This time it's negative, so be it. But charges are unstable. If I have a choice that's not charged at all, in this case here, the negative 2, probably not. But now I have to decide between these two here. Both of them have a negative 1 and plus 1 is 0. 0 plus 1, negative 1. They add up to 0 overall, no problem. If you have to pick, the reason why nitrogen compounds typically are going to be triple bonded, you can try drawing N2 and other amine molecules. Typically, they like having 3 bonds. We're going to add one last rule here. I know these are not real charges, but in this case here, I have N in the middle. On the one side, he's being pulled by N. On the other side, he's being pulled by O. Who's more electronegative between N and O? Hopefully, you were able to say the oxygen, closer to fluorine, higher Z effective. So far in the first diagram, my N has a charge of negative 1, whereas my O is 0. That's sort of like saying the N is actually more electronegative. If anyone were to have the negative, so far I've been leaning towards the N, which is not true. More so, this better diagram here, when I have an N in the middle, it's being tugged on one side by N, on one side by oxygen. I know these are not real charges, but if anyone were supposed to have the charge, I would expect the more electronegative oxygen to have the negative charge. So that's another hint to my disposal here. I can expect both of them have the same formular charges if similar formular charges. Even if it's not similar, you can still do this sort of analysis here. Again, the preferred structure, I might still be wrong. Again, sometimes even formular charges gets it wrong. But if I have similar structures, your preferred structure has the negative formular charge, whoever is negative 1 or negative 2, on the more electronegative atom. In this case here, oxygen is more electronegative. Between N and oxygen, who's supposed to have the negative? I'd imagine this negative 1 here. Both of these would actually contribute to the real picture. Both of them have some say of the real picture, but if I were to bank on just one of them, I would say this second picture, asymmetrical as it is going to be most like what it is in real life. We're going to come back later on and talk about resonance, talk about both of them, sort of some average of them being the real picture, but at this point here, we're going to lean towards this middle picture. Again, you don't need to check formular charges for everything. Sometimes it's very tedious, but again, the more practice you get, the faster you are. We want to actually use it only when it's ambiguous. You can try drawing the S and the 6 fluorines in a chain here. Try putting all the dots on. When you have a correct Lewis diagram, check your formular charges. It's not going to be good as this SF6 molecule. All right. So if you have any questions, just let me know. Thanks, guys.